Riemann sum means that we are not going to use 0. We are going to use 1/4. So we would have 1/4 squared plus 2/4 squared plus 3/4 squared plus, I'm going to go ahead and do dot, 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 so I don't have to write the whole thing out. And we would end at 8/4 squared. Right? And we said in the warm-up that if we had wanted to, we could have written this with some summation notation. Right? So we could have 1/4 the sum from 1 to 8 of I over 4 squared. Because the equation is x squared. So if that equation had been like x cubed, then that would be a cube. Or if it had been like the square root of x, then we'd have a square root of I over 4 for that. Okay? So, definitely we could just figure it out by hand. We could just type it into the calculator. But what I would like for us to do right now is use some shortcut rules for this. Okay? So, if we use shortcut rules for this, first of all, we need to square everything here. So, we're going to have 1/4 the sum from 1 to 8 of I squared over 16. And then that 16 is really kind of in the way right there. So I could pull it out here with the 4 and multiply those together, which is going to give me, is that 64? Yes. It's going to give me 64. Sum from 1 to 8 of just I squared. And then because I have a shortcut rule for I squared, I could make this 1 over 64 times 8 times 8 plus 1 times 2 times 8 plus 1 all over 6. Let's try it without it. Let's see. 8 times 9 times 17 all over 6. I don't want to. I'm going to try it though. Let's see. Let's cancel this 8 with that 64 to make that an 8 right there. So 17 times 9, 63, 15, 153. So we'd have 153 over 48 for that, and I don't think that will reduce. So let's just double check it with the calculator here. Actually, we already did that one, didn't we? We knew the answer. 153 divided by 48 is 3.1875, which is what we got earlier, right? So that is correct. So this definitely makes it doable without a calculator. Maybe not necessarily easier, but definitely doable without a calculator to use those shortcut rules. You could. Yeah, you would need to leave it as a fraction for this one here. All right, so now our goal is not to have 8 rectangles or 20 rectangles or 100 rectangles. It is to have infinite rectangles. So what we are going to be doing here is we need to find the area under the curve using our limit as n approaches infinity. Okay, so this formula here, and we're going to walk through how to use it because I know it's a very confusing looking formula. Here, n, let's point out the parts that we have right here. N right here is our number of rectangles. All right. And we are looking for where n approaches infinity. So we're looking for infinite rectangles, right? F of ci is going to be this deals with the function, so it comes from the function. So plug numbers into the function. And this delta x, that's your change in x, that's your width of the rectangles. Which, as you have more and more and more rectangles, what happens to the width of each rectangle? Smaller and smaller and smaller and smaller. So that delta x right here, your width of your rectangles, is going to be the length of your interval divided by the number of rectangles, divided by n for that. So let's look at the problem for this. Okay, we want to find the area of the region between the graph of the function f of x equals 4x plus 2 and the x-axis over the interval from 0 to 4. Okay, so if we want to find the width of a rectangle, we just take the length of that interval and we divide it by our number of rectangles, right? So our width of each rectangle is going to be, in this case, 4 divided by the number of rectangles. But we don't know the number of rectangles. We want to use as many as possible, right? So we want to say n right here. And this would be our delta x, which is our width of each rectangle. And n right here is our number of rectangles. I'm going to write that down. N equals number of rectangles. Okay, so this becomes a little bit more difficult whenever we don't have a number than it was for the original problem. So let's think about our number line here. We want to go from 0 to 4, right? And we're splitting this into n rectangles. So if we're splitting it into n like when we split it into 8 rectangles, we would take 4 divided by 8, and then we go up by 1/2, right? We'd have 1/2, 2 halves, 3 halves, 4 halves. We are going from 0 to 4, and we're splitting it into n rectangles, which the length of this is 4. We're dividing it by n. So each rectangle is going to have a width of 4 divided by n. Right? What that means is this first rectangle would go from 0 to 4 over n. What would the next tick mark be? It'd be another 4 over n away. What would that be? Miles has got it back there. 8 over n. Because it would be, you're at 4 over n, you're adding another 4 over n to it. Those are common denominators. Just add the top, keep the bottom, right? And then we would have 12n, 12 over n, and 16 over n, and dot, dot, dot. What would we end at? 4n over n, right? Because 4n divided by n would be 4. Okay, so let's think about what we've got to do for this problem. So if we're going to do a right, you always want to do, so, well, let me back up. For the problems we are going to do, because I'm telling you, these can get super complicated, and I used to try to teach more of it, but they can get super complicated. For what I'm going to give you, I'm always going to have the interval start at 0. It doesn't have to always start at 0, but I'm going to have it start at 0, because if it does not, it's hard to do with sums. Also, for what I'm going to give you, we want to always use a right Riemann sum, because if our interval starts at 0, then we don't really want to use 0, because we don't want our, like all of our shortcut rules only work if I equals 1. And if we use the left Riemann sum, we use 0, and then I has to be 0, which means shortcut rules don't work, which means that we would have to do it a different way. So we are always going to see this start at 0, and we are always going to use a right Riemann sum. So if we are using a right Riemann sum, the width of each rectangle is 4 over n. And then we would be finding, we would not use 0 because we're using a right Riemann sum. So we would have f of 4 over n plus f of 8 over n. Oh, I'm sorry. Not 8n over n, just 8 over n. 8 over n and 12 over n and 16 over n and dot, dot, dot. And we would end with f of 4n over n. There. Get rid of that sort of in the way. Is everybody with me there? And it would depend on the value of n, right? So if n is just 1, I'd actually have too much here, right? Because if n is like 4, if we had 4 rectangles, then it would just take, 4 times. If I have 8 rectangles, it would take 8. If I had 25 rectangles, I'd have 25 times. What we're looking for, because we want exact area, is infinite rectangles, which means you can't ever do it by hand, right? Because we couldn't ever physically do that by hand. So, we're going to have to come up with some mathematical reasoning that will allow us to do this without having to do it with brute force. So, let's do one more thing here. This is f of 4 over n, which means 4 over n needs to be plugged into our equation right here, right? So that means whenever we have f of 4 over n, we would have 4 times 4 over n plus 2. And I'm going to put a set of parentheses around that. And then we would have f of 8 over n. So that would be 4 times 8 over n plus 2. And 4 times 12 over n plus 2. And it's okay with you guys if I skip to the dot, dot, dots and don't do 16. And then we'd have 4 times 4n over n plus 2. Okay, does that make sense where I'm getting that from? We're taking the values that we had right here, and we're plugging them into this equation up here for x. That's how I'm getting 4 times 4 over n plus 2. Okay, so we want to write this with summation notation, because if we don't, it's going to be, we can't do it, right? So if we write this with summation notation, we need to look for the value that is changing. So in this expression, most everything stays the same, but what value is changing? That numerator of the fraction. We go from 4 to 8 to 12 to eventually 4n. Now, here's our problem. With summations, I've got to go up by integers. 1, 2, 3, 4, 5. Is this going up by 1, 2, 3, 4, 5? It is not. Not exactly. I mean, I kind of see what you're saying. Like, all of these are increments of 4, right? So, like, sort of like factoring out of 4, which would make this, like, if we factored out of 4, right, then this would just be 1, this would be 2, this would be 3, the next one would be 4, and that would work. The way that I normally do this when I write this summation is rather than, like, factoring it out, I just make it a multiple of 4 right there. So 4 over n, I can just leave out front if I want. I would have, actually, am I supposed to leave that out front? Yeah, I think I can. 4 over n, I equals 1 to n of, we're going to have 4 times, because I want this to count by 4s and not just 1s, I'm going to do 4i divided by n plus 2. Okay, because when I start plugging numbers in, I'll plug in 1. And when I plug in 1, I'll get 4 times 1 over n plus 2. That's this, right? And then I'll plug in 2, and I'll have 4 times 2, which is 8 over n plus 2. And then I'll plug in 3, and I'll get 12, and so forth, right? So this, if I'm going up by a number that's not an integer, then I'm going to have to put that multiple with it. There. So this is our summation notation. So stick with me here. We want to put this over 1. We want to simplify this as much as we can. So just leave that 4 over n out here. Sum from 1 to n of 16i over n plus 2. If I want to think about that 16i over n as 16 over n times I can, right? That's the same. And n is not our variable that is changing. I is the variable that is changing, right? Our I is our index. So that means that this 16 over n can be pulled out of an expression if we need to. So we're going to keep the 4 over n out here. We are going to keep brackets around this. Then we could write this as 16 over n times the sum from 1 to n of I plus the sum from 1 to n of 2. Everybody okay here? All right, so I'm going to leave the 4 over n out here. I've got it now where I've got the sum from 1 to n of I, and I have sum from 1 to n of an integer, and I have shortcut rules for those, which is why we've got these on the board, right? So I can replace this sum from 1 to n of I with my shortcut rule, n times n plus 1 divided by 2. And I can replace the sum from 1 to n of 2 with what? 2n. All right, let's try to clean this up a little bit so that it's a little easier to work with. This n and this n can cancel. So that's going to give me 4 over n. I could also reduce that 16 with that 2, make that an 8 right there. So that would be, that's going to be 8n plus 8. Actually, that can't, denominator canceled, so let's write that big. 8n plus 8 plus 2n. So 4 over n times 10n plus 8 which this is all over 1. So if I want to distribute there, that would be 40n plus 32 over n. Lots of work, right? But reminds me what in the world we're even doing anymore. What's that n stand for? Number. It's our number of rectangles, which we want to be infinite, right? So this should be my area, right? Is this so? Like if I do this problem with 8 rectangles, I could plug in 8. It'd give me the estimate. But I want infinite rectangles. So now I'm going to do the limit as n approaches infinity of 40n plus 32 divided by n. What is that? It's 40. The area under the curve is exactly 40. No, each CC right there. This is a each CC. Divide your coefficients. Could you imagine coming up with this on your own? Like, I mean, I hope maybe some of you followed. It wouldn't surprise me if some of you are not even following me here. Could you imagine discovering this on your own? That blows my mind sometimes. Like, well, different mathematicians did work on different parts of math. So, like, there would have been, like, some stuff about summation a different mathematician had already, like, established. Maybe another mathematician has already proven these shortcut rules. But you are sitting here and you're thinking, what could I do? I need to know the area under this curve. I can imagine thinking I'd like to know the area under that curve, but it seems too hard to find. But being able to come up with how to do this on your own just blows my mind that somebody put all that together. Yeah, it is crazy that Coach Wood came up with this in the 3rd grade. Now, let's back up and do something that's going to make you angry. Okay? If you see this problem on a test question, you should not do what I just did. And we're going to learn some, like, this is limit definition. This is super hard. This is not going to be how we're going to do all of our problems. But we kind of need to understand a little bit of it before we move on to doing our shortcut rules. But if you had this problem and I wouldn't use any shortcut rules. This is what I would do. That graph, let's see, 2, 3, 4. 4x plus 2, what is it? Straight line, right? So, 1, 2, oh gosh, I'm going to have to, the scale on, let's use Desmos because the scale on this is crazy. Let's use Desmos because it's going to be hard to graph on here. Up 4 over 1, so y equals 4x plus 2, and we want our, let's make this go from 0 to 4, and we're probably going to need a y-axis that goes up to maybe 20. That'll be enough right there. So let's do x equals 0 and x equals 4. We're looking for this area under the curve. Did we have to do all that? That is a straight line, right? So if I put in y equals 2 right here, equals 2, sorry. Y equals 2. I could find the area of this rectangle right here. I could find the area of this triangle, right? If I did that, this rectangle is 4 times 2, which is 8. This is 1/2 times 4 times, let's see, what's the height? That goes up to 18 minus 2, 16, which is going to be 32. 32 plus 8 is 40. Right. So And all that. Yeah, all of that. I thought about mentioning it to you before we started, but I was like, they'll be like, Ms. Hyatt, why would you ever even try to do it that way? If there's a better way. So if you get a straight line, use it. Graph it and use the area formula. It is easier to do for sure. But a lot of times you're not going to get a straight line. I started with the straight line just because it's an easier function to work with. And I'm not going to give you anything way too crazy to work with because, again, we're going to learn a better way eventually, a faster way. Because I want you to have a background understanding of this, and they may ask some questions on it, and I want to give everybody a chance of getting those questions right. Now, you might be saying to yourself, Ms. Hyatt, there's still not a chance for me. And that might be true, but we're going to give everybody a little bit of a chance to try it. This is not going to be easy stuff, but I want you to be exposed to it. In college, you also could run into some professors that might spend a lot of time on something like this, proving to you why the shortcuts work. You might not, but you may. So let's get a little taste of it here while you're in here with me rather than later. All right, now I did introduce this notation to you just a little bit yesterday. We are still not really doing this notation, but they're going to use it to ask you for the exact area under the curve. So this notation right here is asking us for the area under the curve of f of x on the interval from a to b. A is your lower bound. Right is your upper bound. And f is just whatever your given equation is. So on some of the questions you're going to have on homework, it's not going to be written out in words like the last problem was. It's just going to say, like for example, that last problem, it would just say, let me do it in red right here. It would do integral from 0 to 4 of 4x plus 2 dx. That's how they would write it for that. That would mean find the area under the curve from 0 to 4 of y equals 4x plus 2. For that. Now, let's see if we can do one more. Okay, now I said I was not going to give you one that didn't start at 0. But this one does not start at 0. So I lied a little bit. But I'm not going to teach you how to do one that does not start at 0. How could we make this work so that it would start at 0 instead? 0 to 2 is going to be different than negative 1 to 1. Let's think about the graph of this function right here. It is an upside down parabola that's been moved up 1. Alright, what do we know about a parabola? It is going to be symmetric, right? So, this area right here should equal this area over here, correct? So, it will be equivalent for me to just do 2 times the integral from 0 to 1 of 1 minus x squared dx. So I can just, rather than doing from negative 1 to 1, I can go from 0 to 1 and just double my answer. Okay, this only works if your graph is symmetric about the y-axis. If you have, I think there is maybe one on your homework that's not 0 to a number, it's going to be a situation like this. Go 0 to the upper bound and then just double your answer for that. Okay, so we really just want to find this like blue area right here. So we're just going to go from 0 to 1. So let's think about our number line. We're going from 0 to 1, which is just a distance of 1, correct? All right, so we would have the width of each interval is going to be 1 divided by n. All right, so what's the next one that we would have? 2 over n, and 3 over n, and 4 over n, and 5 over n, and dot, dot, dot. What's 1 going to be? N over n, which is just 1. So, what we're going to have to do for this is we're going to have to do the width of each rectangle, which is 1 over n. Last time it was 4 over n because we were going from 0 to 4, right? This time it's just 1 over n because we're just going from 0 to 1. If we were going from 0 to 7, it'd be 7 over n, right? And I like to write it this way: f of 1 over n plus f of 2 over n plus f of 3 over n plus dot, 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 f of n over n. You might not need that right there to remind you what to do. So if you skip that step, it's okay. F of x is this 1 minus x squared. All right. So then I like to plug this in. I've got 1 over n. And I've got 1 minus 1 over n squared plus 1 minus 2 over n squared plus 1 minus 3 over n squared plus dot, 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 1 minus n over n squared. So for this, you're going to write your sum. Then you need to turn it into summation notation for this. So this is like that part of the homework where it had those lists and you had to decide how to write it. So you're looking for the value that is changing in the expression. And that would be this part of the fraction right here. It is increasing by integers this time, so we don't have to put like a 4i like we did last time, right? We can just put I for that value. So if we're doing our summation here, we are going to have 1 over n times the summation from 1 to n of 1 minus I over n squared. You can put it on the inside or the outside. It is fine. Whichever place you would like to put it. It can be pulled out on the outside because I is the letter that's changing. So anything else that's like a scalar multiple can be pulled out and n would be included with that. But if you put it on the inside, it is fine also. Okay. So let's work on this a little bit. I've got so your steps, you're trying to do your sum, write it in summation notation. When you get in summation notation, you need shortcuts because you can't do a limit while you still have summation notation. So for this is going to be the sum from 1 to n of 1 minus I squared over n squared, which if I want to write it, I can do 1 over n, make sure you got a bracket there. The sum from 1 to n of I minus, right here, I'm going to do this, n squared, again, is like a scalar multiple, right? I'm going to do 1 over n squared times the sum from 1 to n of I squared. What I'm looking for here is I want this part and this part to just be an I squared or I cubed, so I can plug that in. Yes? We replace this, whenever we did our sum, that number that was just increasing by 1 each time, we replaced it with an I in our sum. Which I? Oh, I'm sorry, that should be a 1. Thank you. This I right here should be a 1. That should be a 1. Does that make more sense now? Sorry. A 1. Okay. So, shortcut rules. I'm going to leave my 1 over n out front. Okay? What is the shortcut rule for the sum from 1 to n of 1? 1n. Okay? If you have a number, it's just 1 times that, or n times that number. Okay? And then we've got 1 over n squared. And I've got to use the shortcut rule for I squared. Now, I'm going to do something right here. And I'm going to use my calculator because we're out of time. I'm going to cheat and expand this on the calculator. Expand. It is going to make our lives easier. If rather than using, because if we use that formula right there, we're going to have to expand all of that. Why is it not working? I need a multiplication symbol right there. Come on. I've done it faster by hand. Alright, this is equal to 2x to the third plus 3x squared plus x over 6. Okay, I'm going to write that down right there, and I'm going to plug that in instead of plugging in the original because I'm just going to have to multiply it out if I do that. So, I've got 2x cubed plus 3x squared plus x over 6. I'm going to also erase that 1 in front of that n right there because it's unnecessary and it makes it look like natural log, and it's not natural log. Okay, so I got to put all this stuff together. I used x's instead of n's. Pretend those are n's. Time is running short. Okay, so I've got 1 over n. I got n over 1. I can multiply this through. I'll get 2n cubed plus 3n squared plus n over 6n squared. To put those together, I need to multiply this by n squared. Actually, I need to multiply it by 6n squared on top and bottom. Right? Because we've got to have common denominators to put those two things together. So I will have 1 over n times 6n to the third. I got to subtract all of this stuff here to n cubed plus 3n squared plus n over 6n squared, which is going to be, we'll distribute that negative. I will get 4n cubed minus 3n squared minus n over, I'm going to go ahead and multiply this 1 over n in here as well, over 6n cubed. If you're doing these problems and you do not get the same variable, like same degree on top and bottom, you've messed up somewhere. Because what should happen now, if you can make it to this point, if you get to this point, you're about done. We need to do limit as n approaches infinity of this. You should every time have exponents of the same top and bottom. Divide coefficients. No. Here, we get 2/3 for this. Alright, I know this is rough. I'm only going to make you do it today. You've got 4 problems tonight for homework. It is posted on Canvas. I'll pull it up right here. Oh yeah. We didn't have time to do that today, did we? Yes, it is. I will post a video for that one. You guys have a preference on which one? Or you want me to pick what I think is the most difficult? Yeah. Yeah. Any preferences?
That's what I can do.
Good, thank you. All right. It's 47, 49, 50, and 54. I realize you may have a little hard time getting to the end on this. At least start it. Try something, okay? On those. Oh, we need to multiply our answer by 2 on that last problem. Because we only did 0 to 1, and it was supposed to be negative 1 to 1, so it was 4/3. I told you it was going to get worse before it got better.